Okay, thank you, Mr. Chairman. I'm Tomoo Nakai. Today's my talk is a sensitive thin-film magnetic impedance sensor system used in strong normal magnetic field for detecting small particles. I'd like to introduce myself first. I'm a general researcher of the Industrial Technology Institute, Miyagi Prefecture Government. This institute is an office of local government for the purpose of promotion of local industry, not university. So we have almost 60 persons in this institute, including researcher and equipment analysis and technical supporting staff. I think that it's very rare that the research staff of such local institute would participate in international conference. So I'm very happy, and it's very great honor to talk here. This is the outline of my presentation. This sheet shows the fundamentals of my presentation. These schematics show a magnetic momentum in a thin-film magnetic sheet. A magnetic momentum in a soft magnetic thin film behaves as if it is restricted in two-dimensional space due to a demagnetizing force along the thickness direction. The magnetic momentum in the thin film clustered and forms a certain pattern of magnetic domain, which is dominated by magnetic energy such as Bohr energy, exchange energy, anisotropy energy, and CMAN energy. The domain is also strongly affected by a shape of thin film. This sheet shows the proposal and objectives of this work. My talk is concerning about a sensing system which can detect small-sized magnetic particles. These schematics show an outline of our proposed method. The technical point of our proposed method is an application of strong normal magnetic field in the measurement area, which is including sensor element and particles. The magnetic particles are magnetized in this strong field and detected by the thin film sensor at the same time of magnetization. These are the schematics of a measurement system. A strong magnetic field in the normal direction is generated by strong magnets, and the thin film sensor are set in the magnetic field as a sensor array. In this system, high sensitivity thin film sensor is used, and its sensing direction is arranging along the horizontal direction. The reason is why the sensor is placed in the direction of horizontal direction is because the thin film sensor has a tolerance against a strong magnetic field along the surface normal direction of the sensor field. It's because due to the demagnetizing force. From here, the aim of this study is shown. We are trying to apply the sensing system to detect magnetic biomarker or magnetic nanoparticles in chemical solutions. The main schematic of this sheet shows a structural drawing of our development. The upper right figure shows a magnetization curve of magnetic small particles. We can see that the particle needs a strong magnetic field in order to make it saturation magnetization. And it's also shown that the remanence is very small. Then this type of magnetic nanoparticles are difficult to detect using a conventional method, such as using AC field pickup coil and sensing a residual magnetism. In order to detect such particles using a proposed method with high sensitivity, a stronger magnetic field is needed for improving the sensitivity. The stronger magnetization of a particle makes a stronger field as a sensor position. Then the target strength of our research set as 0.35 Tesla normal field, which can make the magnetic particles, nanoparticles, almost saturation magnetization. In the following presentation, we will show a confirmation of the tolerance of the sensor against this strong normal magnetic field, and also a sensor property in such strong normal field. This is a measurement apparatus I made for this study. For the purpose of confirming the tolerance against the normal magnetic field and also measuring the sensor property in the field, a measurement apparatus which can apply strong vertical field was made. It was designed based on a car microscope system. The vertical field was generated by an electromagnet, which was an attachment of the car microscope. The sensor with driving circuit and the coil for controlling the horizontal magnetic field was set between the pole piece of the vertical magnet. The single sensor was inserted as a sensor plane fit to the horizontal plane. The upper right photo shows a full view of the measurement system, and the lower right photo shows an enlarged view of the electromagnets and sensor fitted on the car microscope. This sheet shows the sensor element, the simple magnetic impedance sensor, and the driving electric circuit was our institute's own making. The sensor was made by an amorphous cobalt neodymium zirconium soft magnetic thin film, having an easy access of magnetic anisotropy in the direction of the width direction of the element. The sensor has a meander configuration and connected to the printed circuit board, and then it was connected to a driving circuit. The magnetic domain at zero external field is shown on the right, and the impedance variation as a function of the sensing field is shown above. This profile of impedance variation is a typical one of the thin film magnetic impedance sensor. The sensing direction of the sensor element was in plane length direction, x direction. From here, the results are shown. This sheet shows the variation of sensor output as a function of the applied normal field. The left figure shows variations of sensor output as a function of sensing magnetic field. The normal magnetic field was a parameter, and the normal field varied from 0 to 0.35 Tesla. The horizontal magnetic field, which corresponds to a sensing field, Hx, was controlled by the horizontal coil. The profile of this sensor output is a vertical inversion of the element impedance previously shown. The reason is that the signal level coming out from the sensor element is inversely proportional to its impedance. The right figure shows the variation range and effective sensitivity, which are obtained from the left result. The variation range means the difference between the maximum and the minimum output value. The effective sensitivity means the maximum inclination dB of the sensor property. It means sensitivity. The results show that both values monotonic decrease as increasing the normal magnetic field. The sensitivity at 0.35 Tesla normal field decrease in 50% relative to the one without normal field. But even if the sensitivity decreases, we can say that the sensor works in 0.35 Tesla. This sheet shows the observation result of magnetic domain. The observation was carried out while the previous impedance measurement was done. It is done within static 0.3 Tesla normal field. This sheet shows that the domain variation when the horizontal field varied from 0 to 2.6 millitesla. From this result, the variation of magnetic domain in 0.3 Tesla normal field was qualitatively the same as the one in the zero normal field. The strike domain, which is called the Landau-Lifshitz domain at zero horizontal field, gradually changes with domain width and finally erased as increasing the sensing field. This domain variation is also the ordinary one of the magnetic impedance sensor, which is observed without normal field. This sheet shows an apparatus of sensitivity evaluation. A small alternating field was generated by a solenoid coil in the horizontal direction. This measurement was carried out by applying both normal field of 0.3 Tesla and the bias field. The magnetic field vector for measurement is shown in the middle. A schematic explanation of this measurement is shown in the lower left figure. The input alternating small field was converted to an output signal at the sensor bias point. This sheet shows the measured results when 1.6 cross 10 to minus 7 Tesla at 5 Hz was applied within 0.3 Tesla strong normal field. The left figure shows an oscilloscope waveform, and the right figure shows a frequency domain spectrum of the same signal. In both figures, the sensing 5 Hz signal is distinctively observed. When the applied field decreases to 5 cross 10 to minus 8 Tesla, the measured spectrum changes as this sheet. We can see that the 5 Hz peak of the signal was distinctively sticking out from the background level. As a result, our thin film sensing system can detect a 7 digits lower signal within 0.3 Tesla static normal field. This is a summary of my presentation. Thank you for your attention.